In previous videos, we were discussing things like a positive and negative charge that would have a force between them. So if you had these two charged like this and you let them go, the negative charge would be attracted to the positive charge and the positive charge would be attracted to the negative charge. In other words, the opposites attract that we know about. We also discussed things like about how in conductors, if you bring a positive rod near a conductor, it'll pull all of the electrons in the conductor to this lower surface here, leaving a net negative charge along this surface of the conductor and a net positive charge, or a deficiency of a negative charge, is over there. So the question that we're going to discuss, or the issue we're going to discuss in this particular video then, is what is it that causes this to happen? Because if you look at, say, either one of these cases here, there's no contact between these two charges right here. There's just nothing but, in this case here, say, empty space between them. So what is it that causes the negative charge to attract to the positive charge, or the positive charge to attract to the negative charges? There's no ropes, there's no pushing or pulling or no contact or anything. So how is it that these things sort of find themselves attracted to each other, and how is it that they actually start to move towards each other? Likewise, in the case over here, all we did was bring a positively charged rod near this conductor over here. There's nothing but empty space in between. So what is it about this space or this rod or the conductor that causes the electron sort of to move to the lower end of the conductor, to be on the edge like that? What is it that exists in this space right here? How does it happen? Again, there's no ropes, there's no contact, there doesn't seem to be anything happening. So that's what our question is that we're going to talk about in this particular video. And of course the answer to what is it that exists between the rod and the conductor, or between the two charges, is something called the electric field. So let's just start out this way. Think about a problem like this. Suppose I had a negative charge sitting here like this, and there was a positive charge over here, and I launched the positive charge this way with some velocity. We'll just call it v. You know how fast it would be. You can look at some typical speeds in your books there, but we're going to launch that way. What would you expect this positive charge to do? Would you expect it to continue along a straight path like that? Or would you think of it moving some other path? Turns out that what will happen is, of course, opposites attract, and that still holds even though this charge is moving. So as the charge moves this way, it will be attracted to the negative charge, and depending on its speed, it will not follow this trajectory, a straight trajectory. It will be affected by the negative charge. It'll actually get pulled down like this. It'll probably follow a trajectory more like that. Okay, it'll go like this because as it moves, it's attracted to the negative charge, so it'll curve down like that. So again, the issue is in front of us then, is what is it that happens in this region right here that actually causes this positive charge here that would like to just move straight to the right to actually curve and bend down towards the negative charge like that. And it turns out it's something called the electric field. So in the first sort of description of our electric field here, here's what happens. When you have something like a negative charge like this, it turns out that if you have a negative charge just sitting there, the entire universe, all of the space, including the whole universe around this negative charge, will be filled with something called the electric field. And it turns out that it's going to look, for a charge like this, it's going to look something like this. It's going to look like a big starfish like this, or a big star like that, and the electric field lines are actually going to point inwards towards the charge like that. And these electric field lines fill in the entire space, the entire universe around this negative charge will be filled with these electric field lines. You can actually label them E if you want. Those are electric field lines like that. What do they look like for a positive charge? Well, for a positive charge, it looks kind of similar like this. We can draw a positive charge right here. And just because that positive charge sits there like that, it also will fill the entire universe, or all the space around it, with its own electric field lines like that. So here are all the electric field lines due to the positive charge, and because it's positive, the electric field lines actually point away from it like that. Something like this, and this, and this. There's all these arrows. These electric fields just fill the entire universe around this positive charge like that with these electric field lines. So there's sort of your first fact for you there about electric fields, that whenever you have a positive charge, electric field lines will always be emanating in a direction away from the charge. When you have a negative charge, there'll be electric field lines that are always going in towards the charge. So out of positive into negative is the way I remember it. You might also see sometimes in your book, positive charges are sometimes called sources of electric fields because the electric field lines come out of them, and negative charges are sometimes called sinks of the electric field because the electric field seems to disappear in them. So however you want to think about it, just remember electric field lines always go out of positive charges and go into negative charges. So that's sort of the nature. This is what actually exists between two charges to cause these effects to happen that we've been witnessing. So let's just go back then to two charges near each other and see if we can describe why they attract. So here's a positive like this, Here's a negative right here. And the question that was before us earlier was, what is it that appears in here that causes this positive charge to be attracted to the negative charge? And well, of course, it is the electric field line. So as we just discussed, there's these lines that fill all of the universe around the negative charge, like this. And they go into the negative charge. These are the negative charge's electric field lines, like this, going in like that. And of course, there is an electric field line that goes right through the positive charges, because they exist in all space around it like that. So it looks like this, and like this, and like this. So here's the negative charge with its electric field lines going into it, and one of its electric field lines happens to go through the space where the positive charge exists. So to answer that question of what exists between the two charges that causes the attraction to happen, is you see it now. The electric field line, due to the negative charge, is what exists in that space. And so this positive charge is affected by this electric field line, which is coming from that negative charge here. And so that is what actually pulls the charges together. Now you may be thinking, well, wait a minute. I thought it was Coulomb's law that causes two charges to attract each other. I thought it was Q1, Q2 over R squared. And you're right about that. And there's an R hat in here, and we'll put a vector over it. And of course, just a quick review of what that R hat means. We saw that in a different video here. In this case here, once again, the orientation between the charges isn't all along the X or Y axis, but it's sort of down a diagonal. So this downwards direction here would be our R hat. R hat's like a placeholder for direction. Okay, just a little bit of review there. Isn't too much about what we're talking about here. So you look at this and go, well, which is which? Which is the Q1 and the Q2? It doesn't really matter, but we do have to get a bit more specific with it now. Why don't we go ahead and call the negative charge here our Q1, and we'll call our positive charge here our Q2. Now, sometimes if you start leafing through your physics textbook and stuff, there's a bit of a difference here in what the roles the charges play. In particular here, because our focal point is on Q1 here, this is sort of causing the E field due to Q1 is what we're sort of analyzing is affecting this positive charge, Q2 over here. So sometimes Q1 here will be called the source charge, because it is the source of the electric field that's causing the dynamics of our problem to happen here. Like if this negative charge wasn't here, the positive charge would just be sitting there. It would not be attracted. Nothing would happen. So we sort of play it like that. Now, what role does the positive charge play? Well, the positive charge is the one that we're testing the environment with. Like if we put the positive charge here and we notice that it starts moving this way, we must conclude there must be an electric field there. So sometimes this Q2 here is called the test charge. It's called the test charge because we use the positive charge to test the local environment to determine that maybe there is an electric field in there. And so if this is the case like this, well, how does everything sort of jive together? Well, what we do for electric field is we use a key relationship, namely that electric field is none other than the force divided by Q2. So it's going to look something like this. The electric field then would be K times Q1 over R squared. Here's the force law right here. And all we have to do is divide the force law by Q2 to get the electric field. So electric field and force are definitely related, but if you look at the two resulting equations, the K is still here, the R squared is still there, but what remains in the electric field equation right here is not the test charge, but this is that source charge once again. Because remember, it's the source charge which fills space all around it with an electric field, this electric field. Then we can go onwards to see what effects the electric field might have, but in the case of this, it's the source charge that sort of generates that electric field. And that's what fills space all around it with a field and causes our problem to happen, say, the way it does. So you always divide the force there by the magnitude of the test charge right there to get the net electric field. Let's just look at that a little bit more closely here. So once again, we'll look at it like this. The difference between the source and the test charge is sort of something that works like this. So suppose I have a positive charge like this, and I send it going this way with some speed v like that. Okay? If the charge sort of keeps going in this straight direction, what can you conclude about the space all around the charge? Well, I would conclude that there is no electric field here, because this charge is moving in the straight direction. There doesn't seem to be anything attracting it. It's not being pushed or pulled or anything like that. But suppose in another case, I launched a test charge like this. Instead of going straight across like that, suppose the charge started to go up that way, like that. What would you conclude about this space around here? Well, I would conclude that there's probably a positive charge in here somewhere. Because although this charge would like to go straight like that, it actually curves up and to the right like that, because there's a positive charge here, which is, as we know from Coulomb's law, is pushing away from it. Like charges repel each other, so this charge doesn't get repelled away. So that's why this other charge here is always called the test charge. Because we put it in some region and we just watch what it does in its motion, whether it's launched or not. It's the test charge. We're testing the region to see if it goes straight, we conclude there's no field. If it goes up like this, we conclude there must be a positive charge here. And in the other case, what if it went down like this? Then you would conclude that there's a negative charge here. But all that's a ramification of using this as a test charge. We're testing the area to see if there's an electric field. Now, to just reverse the roles of them again, let's go ahead and leave this positive charge right here. We'll launch it this way like this. It might go straight, it might bend up, it might bend down. You might be asking why. Oh, this space must be filled with electric field at some point to cause all this to happen. Well, what we do now is we go, okay, the charge over here then, this is the source charge. This is the charge that's causing all the problems. This is the one that's filling space around it with an electric field, causing this charge to deflect up or deflect down, depending on what the sign of the source charge is. So you put the source charge in there, and as we said earlier, all of space around this source charge is filled with its electric field lines. And we know now the electric field lines go out of positive charges and into negative charges. So I'll draw arrows in all these lines, pointing away, pointing away, pointing away like that, all pointing away. Let's see, do I have them all covered? Yeah, I do. And there is an electric field line that happens to go through this charge, and this is the one that's going to cause that upwards deflection like that. So as it moves, it'll always encounter another electric field line because of this source charge, causing it to deflect upwards like that. So that's why this is called the source charge right here. So all told then, the way we start to analyze problems and when we're dealing with the electric field isn't so much about the interaction between two charges, the test charge and the source charge, but really we can get a lot of understanding and a lot of work done on this if we just think about the source charge. So if we just think, hey, I have a positive charge like this, and I have electric field lines that fill the entire universe around that positive charge. If you want to know what the strength of this electric field is, you would just write it as K times Q over R squared. So Q is the amount of charge that is placed here. It could be just one charge of one proton, or it could be some of these other numbers you'll encounter in your textbook. It could be something like maybe positive 10 nanocoulombs, or it could be 1.6 times 10 to the minus 19 coulombs, the charge on a proton. It could be some of these numbers, but the point is that you place some quantity of charge here. You multiply by K here, which is 9 times 10 to the 9th. That's that constant that we learned about in another video. And the R here is how far you are away from the charge. So I keep saying that it fills all of the universe with these electric field lines, but of course it matters how far you are. So the electric field is going to be really strong in regions like this because we're really close to the charge in regions like this, but it's going to get much weaker as we go farther away, like way out here or way out here, because of this R squared dependence in there. But in either case here, this tells you how strong the electric field is around source charge. Of course, if the source charge was gone, the electric field would be zero because Q would be zero, but that's the nature of the game. The source charge generates the electric field. Then, of course, if we put a test charge somewhere in this region, suppose we put a negative charge right there. The negative charge could be moving, it could not be moving, but what we'd expect from Coulomb's law is opposites attract. We'd expect this negative charge to fly in towards the positive charge, and that's what it'll do, but it's flying in because it's caught in the electric field of this source charge right here. So remember, this is the test charge over here, this is the source charge down here, and that's sort of the way the two interact.